So the next part of this, as a key bit of evolution of understanding how chemistry works on a fundamental level, is to talk about atomic theory. And this is going to be something we talk about in chapter 4 and then come back to in chapter 11 with modern atomic theory. And so getting started with this, we're going to go way back in time. And I can't even quite imagine being the people understanding this in these years. So we're talking long, long ago. The idea of law of constant composition came about with Joseph Proust. And so what basically this is saying is understanding what we know about a compound, that it has the same proportions or fixed ratios. And we didn't know what an atom was at this point, but we did know that if you took the percentage by mass in, say, water, that there's always 8 grams of oxygen for every 1 gram of hydrogen. And so we knew that there was this constant composition of these compounds. Understanding a little bit more what made up these compounds and moving on in the next decade or so, we had John Dalton. And Dalton came up with Dalton's atomic theory. And a lot of this stays the same. A lot of this is incorporated into a modern atomic theory, and some of it has just been fixed a little bit. So these basic postulates here is that the first one is that elements, if we're trying to figure out what atoms are, elements are made up of tiny indivisible particles called atoms. Well, what Dalton didn't know is that there's subatomic particles. And so that's the fix, right? Is that's the asterisk, that you can actually divide atoms. And there are subatomic particles that are making that up. So examples of that would be an electron or a proton, which we're going to talk about. The next postulate, or the next idea of Dalton's theory here, is that all atoms of an element are identical. And so an atom of carbon is just the same as every other atom of carbon. Well, we know that that's not actually true now. We didn't know it at the time. So the correction is that these atoms of elements are the same in a lot of ways, but one way can be different. So we know that they have the same number of protons in their nucleus, but they sometimes have a different mass. And so what we're talking about here are isotopes. And you might have heard about radioactive isotopes. And isotopes are a naturally occurring thing. We'll talk more about these subatomic particles and the corrections to Dalton's theory here. So the next ones from this point on, you'll notice there's no red in Dalton's work, so there's no corrections. These ones, his work holds. And so atoms of one element will differ in mass, properties, and mass and property, from other atoms of another element. And so carbon is not the same as oxygen. And so we can have some consistencies, but there's very fundamental differences between the different elements on the periodic table. The next one is that atoms combine in whole number ratios to form compounds. And so that idea of fixed ratios, it was building on Proust's law of constant composition, but bringing in this idea of atoms now, not just mass, but actual atoms are the fixed units. The last one here is that atoms are indivisible by chemical processes. Atoms are not created or destroyed in a chemical reaction. They're just rearranged, they're regrouped the way that they're bonded. And so this idea of carbon and oxygen makes carbon dioxide. So that idea. There's a lot of others, and we're going to get through a lot of nomenclature in chapter 5 and then chemical equations in chapter 6. So that's where we're getting to. So here we've got the words that give us a building block so that we can understand what we're talking about, and then we'll get into the language. So this is just the corrections that I think I've already talked about at the top. So if it's in red here, those were the things that were wrong with Dalton's work, but I think he did pretty good. He got 3 out of 5, better than I do with his tools probably. So now that we have this idea of constant composition and what a compound is, this idea of fixed ratios, and we have basic understanding of what an atom is, really what we're going to do here is talk about chemical formulas. And like I said, this is built on further in chapter 5, but chemical formulas, you already know some. So water H2O is a chemical formula. I've already written another one that you probably already know. CO2 is a chemical formula. That's carbon dioxide. And so this is chemical formulas symbolically express the number of atoms of each element in a compound. They represent that fixed ratio sometimes. So the number of atoms is indicated by a subscript following the symbols or the element's symbol. If there's no subscript, then we know that there's one. And so here, this example, water has 2 hydrogen atoms and 1 oxygen atom. If I do my example here, I would have 1 carbon atom and 2 oxygen atoms. The rest ones are already written here, so we can go through sodium carbonate. So we'd have 2 sodiums, we'd have 1 carbon, and we'd have 3 oxygens. So these ones are pretty straightforward. In the world of chemistry, there are further complications to this in that sometimes you can have units. And so sometimes there's brackets or parentheses to show a unit. And so what we're talking about here is PO4. And so what we've got is, I'm going to just kind of draw it out. We've got 3 barium atoms, and we've got 2 units of the phosphate group, which is a PO4 and a PO4. And if we chemically bond these all together somehow, which we're not even ready to talk about yet, that's what we're talking about. And so we've got a certain number of units. And so we could go through and figure out how many of each kind we'd have. So we'd have 3 bariums, we'd have 2 phosphates. It's like this 2 is being distributed here. And then we have 2 groups of 4 oxygens, so we have 8 oxygens total. That's 2 times 4 in the brackets. And so I don't think you need to draw it out every single time. This idea of understanding what this nomenclature means, the way it's written as a chemical compound or as a formula, can be really useful. So here's one for us to try. I'll switch back to the blue. We want to try and figure out how many atoms of each element are present in TNT, which is given to us right here. Take your time. It's not complicated math. It is easy to make mistakes. And so just work your way through. So we've got 6 down here to do as examples. Maybe I'll throw the answers up and you can check as you go. Oops, I'll do it with the symbols. Maybe that's a good way to get used to doing these. That's the way I've done it before. You can write out the name if you like that, but you can see how the shorthand symbols can be really helpful. Two down here are drawn out, kind of like what I was doing with the other example at the top there. Take your time when you see those parentheses or the brackets around a unit, because it kind of distributes through. I feel like I'm going to make a mistake on this one. So I'm just going to cheat and look at my answer key. You take your time in sorting it out. Makes you happy to come back to the pictures. The last 3 examples, I think, are a little bit simpler in a sense because they just spell it out. So if we have 4 phosphorus atoms and 10 oxygen atoms, the chemical formula would look like that. 1 uranium atom and 6 fluorine atoms would look like that. 1 aluminum atom and 3 chlorines would look like that. There's lots more nomenclature in chapter 5, which is really more about predicting how you write these things, but that's where we're going to leave it for here.